6.10. Aqueous feed containing A, Ca0 is equal to 2 moles per liter, enters a plug flow reactor of 10 liter volume, which has a provision of recycling the portion of the flowing stream. The reaction stoichiometry and the kinetics are given. A gives R. This minus RA is equal to KCACR. So this is rate law of autocatalytic reaction. So A gives R at the beginning, then once the reaction starts, it is A plus R giving R plus R. So for that, it is minus R is equal to KCACR. We wish to get 96% conversion. Should we use the recycle stream? If so, at what value should we set the recycle flow rate so that we obtain the highest production rate? And what volumetric feed rate can we process to this conversion in the reactor? So we know XAI is equal to R by R plus 1 into XAF, minus RA is one into CACR, that is given. So minus RA, in this case it is Ca0 into 1 minus XA multiplied by Ca0 XA. So Ca0 value is 2. So 2 into 2, 4. So Ca0 is 2, Ca0 is 2. So this becomes 4. 4 XA into 1 minus XA. So we get one equation of minus RA from the rate law as 4 XA into 1 minus XA. So 1 upon minus RA is 1 upon 4 XA into 1 minus XA. Now we use the recycle model. 1 upon minus RA at XAI is equal to integral XAI to XAF dXA by minus RA divided by XAF to XAF minus XAI. This we have already derived, okay, for autocatalytic reactions. So dXA by minus RA is 4XA into 1 minus XA. Okay, XAF is 96%. 96% conversion is desired. So XAF is substituted 96. Here XAF is 0.96. So numerator 1 upon 4 is taken out. So 1 upon 4 is minus, it's 0.25, that is taken outside integration. 0.96 and XAI, R will be some constant value, and from that XAI will be some constant value for one recycle ratio, one particular recycle ratio. So this we have taken outside. dXA by XA into 1 minus XA. XAI to XAF is 0.96. This can be evaluated, and after substituting the limits of integration, this comes out to be ln of 1 minus XAI into 0.96 divided by 1 minus 0.96 into XAI. Okay, this you will split into partial fractions, and then we have done it number of times. So this you have to find out, evaluate this integral. So 1 upon minus RA evaluated XAI becomes this term 0.25 divided by 0.96 minus XAI into ln of this integral is ln of 1 minus XAI into 0.96 divided by 1 minus 0.96 into XAI. So this is second equation. So these two equations we should use, and we want to find out the value of XAI, okay, from here, so that it matches with the equation 1. So what we will do, for different recycle ratios I am taking, so there is provision for recycling. Question is, should we use the recycle stream? If so, what value should we set so that the recycle flow rate so as to obtain the highest production rate? Now you know XAI is a function of R. It is R by R plus 1 into XAF. So for different values of R, you go on calculating XAI values. R by R plus 1 into XAF, and that is fixed as 0.96. So these values we have found out. So from first equation, rate law, 1 upon minus RA is 1 upon 4 XA into 1 minus XA. So using this, you find out these values, and 1 upon minus Ra at some xai value, this value, go on substituting the values of. Now these xai values which have been calculated here, we are using here, and here we use xa is equal to xai, so same value, and you will find these are trial and error calculations. So at recycle ratio of 0.8, xai comes out to be 0.21, and these two equations are almost match, 1.507, 1.501, so almost matching. So we say that at xai is equal to 0.21 and corresponding recycle ratio of 0.2, we are getting the optimum value for this autocatalytic reaction. Same thing graphically also. You plot equation 1 and equation 2 here. Okay. So equation 2 is this. Equation 1 starting from 3.1 to 1 point, this is almost constant, and here it crosses. So that is 1.507 or 1.5 you can say, and this gives you recycle ratio of 0.28. So you will operate at recycle ratio of 0.28, corresponding value of xai will be 0.21. So 96% conversion will get the highest production rate at recycle ratio of 0.28. At this value of recycle ratio R, xai will be 0.21. So you can calculate the volumetric feed rate V, which can be processed to get the maximum feed rate. So recycle ratio, recycle reactor equation, model equation, V by Fa0 is R plus 1 into integral dxa by 4xa 1 minus xa. This is minus Ra for this particular problem. So xai is 0.21, 0.21 to 0.96. This integral we have already solved earlier. Just substitute the values. V by Fa0 you get as 1.441. So Fa0 value will be V by this V by 0. So V is 10 given, enters a PFR of 10 liters. So it comes out to be 6.94 moles per minute. So V, small v is Fa0 by Ca0. So 6.94 by 2 is 3.47 liters per minute. Ca0 is 2. So we can treat 3.47 liters per minute at the best recycle ratio of 0.28 to achieve the 96% conversion for the given kinetics.